Hi, and welcome to the Chicago Pneumatech and Pneumatic Corporation webinar. Okay, right now I'd like to introduce today's presenter, Ben Smith. Ben has 5 years of experience working in the compressed air industry. He has specialized in the air treatment side of the business and has established himself as an expert in the field. Ben is the current product marketing manager for Pneumatech and Chicago Pneumatic brands. Ben, welcome to today's event. And with that, I'm going to pass things over to you to get us started. So Ben, go right ahead.
Hello, my name is Ben Smith. I am the product marketing manager for Chicago Pneumatic and Pneumatech. Today we're going to be looking at compressed air, your most expensive utility. First of all, I want to say welcome to everyone. Thank you very much for taking the time out of your day to view this webinar and attend with us. If you have any questions during or after the presentation, you can always email us or send us a chat. We will have a brief Q&A after the webinar, the live webinar. But if you're watching this on demand, you can always visit us www.pneumatech.com or www.cp.com. As you may have noticed so far, we are two different brands of the same company. We're the same company, but we carry two different brands. Chicago Pneumatic is our air generation brand, and with Chicago Pneumatic, we deal with piston compressors. We also have rotary screw compressors, both fixed and variable speed. We also have oil-free scroll compressors, and we have compressors from 2 horsepower all the way up to 500 horsepower. On the Pneumatech side of things, this is our quality air or air treatment side of the business. And with Pneumatech, we do a lot of different things. We do nitrogen and oxygen generators. We do refrigerated dryers, both cycling and non-cycling. We have a large line of filters. We also do desiccant dryers, carbon towers, and large desiccant dryers, all the way up to 6,600 CFM. So today we're going to go over a few things. We'll do just a brief video that goes over compressed air as a kind of an overview. We will do a few terms that we'll be using throughout the presentation that you should be familiar with. We'll also look at the total cost of ownership for a compressed air system. How much does the compressed air cost? And that's on like a volumetric flow rate. We'll also then start talking about how can you reduce the cost that your compressed air system is costing you. So we'll look at reducing the flow, we'll look at matching your supply with the demand, how much you use, and then as well as lowering the pressure of your system.
"21% oxygen, 78% nitrogen, 1% gases such as argon and carbon dioxide, and minute amounts of trace gases. Together, they form air. Because of their low density, gases such as air can be compressed, unlike liquids. Compression forces the air molecules closer together, increasing the density. Air pressure can be expressed in pounds per square inch, or PSI. The first way to compress air is by displacement. This means enclosing an amount of air and reducing its volume, like in a bicycle pump or a piston compressor. The air volume can be reduced in other ways as well. By rotating screws, gradually decreasing the space between them, or by tooth-type screws or scrolls. A second way to compress air is dynamic compression. Air is drawn into a rapidly rotating impeller and accelerates. The kinetic energy is then transformed into pressure as the air slows down by expansion. Compressed air is a useful resource in virtually every manufacturing process. It can produce motion and exert force, such as in pneumatically powered tools or machines. We then call it energy air. It's a main power source on many construction sites, as well as in remote locations, such as drill rigs or on ships. It powers braking systems and opens train doors. When air is part of a production process, we refer to it as active air. It conveys tons of powders, pellets, and grains. It's used to maintain pipelines and provides the pressure for cleaning and paint spraying. Overpressure keeps out impurities from clean rooms and critical production areas. Compressed air is also a vital component in fermentation, combustion, liquefaction, and refrigeration. It's used for gas treatment or air separation. Because the gases forming air are not mixed chemically, they can be separated into oxygen, nitrogen, and argon. Compressed air also provides oxygen to water purification and blows plastics into shape. It helps patients breathe and drives precision tools in a medical environment. In short, compressed air plays a part in countless products and services we enjoy every day. Air has a capacity to convey objects. It also conveys very small components such as solid particles, microorganisms, and water vapor. As air is compressed, the relative particle content and humidity increases dramatically, causing water vapor to condensate, potentially leading to contamination of equipment or products. That's why sophisticated equipment accompanies the compressor itself, filtering impurities, draining the water condensate, ensuring clean, dry air of the highest quality. An American-born leader in compressed air is Chicago Pneumatic. People, passion, performance.
All right, so a few terms that we want to talk about today are flow rates. So you may hear SCFM, or standard cubic feet per minute. Now that's like, it's a way for us to take a volumetric flow rate and equate it with basically a mass flow rate. So what we say is we're at sea level, at standard temperature and pressure, this is the number of cubic feet of air that would be going through that system if basically conditions were perfect, if you are at standard temperature and pressure. Now, when you're sizing your actual compressor, a lot of times you'll hear ACFM, or actual cubic feet per minute. Now, the actual cubic feet per minute is adjusted for your conditions. So when we're talking about sizing a compressor, you need to know what the actual cubic feet per minute it's going to be pulling in, dependent on whether you're at altitude or there's some temperature differences other than what we usually have for standard temperature and pressure. So what you'll see a lot of the time is that compressors will be sized for ACFM, actual cubic feet per minute, because it's dependent on the conditions. But once that air enters the air system, it becomes standard. We convert that to standard cubic feet per minute, and that is how we size the other parts of our air system. We're also going to talk about pressure. System pressure is basically just the force exerted on a compressed air network to perform the needed task the system requires. So that's just fancy for we're using this air to run a sandblaster, or we're using it to paint some components. This is the pressure that we need. Now, pressure drop, that is a term that we use when we talk about the difference between the inlet pressure at a piece of equipment and the outlet pressure at a piece of equipment. Usually when we're going to be talking about it in here, we're going to be talking about the pressure drop across different air treatment devices. So whether it be dryers or filters or any other piece of equipment that you may need to prep the air, regulators, lubricators, that kind of thing. Something a lot of people don't know about compressed air systems is that when we start talking about the total cost of ownership, so basically how much does it cost you to own this equipment for the life of the equipment, and something that they don't really realize is that 75% of the total cost of ownership is energy consumption. Only 25% then makes up your installation cost, your maintenance fees, and your initial investment. So a lot of times people are a little leery about spending money on energy-saving features because it's of course a little more expensive for those energy-saving features. But when you look at it over the long-term life of the compressor, you will find for not only the compressor but other pieces of equipment in that compressed air system that you can greatly reduce the total cost of ownership by investing in some energy-saving practices, as well as optimizing your compressed air system. So how much does compressed air cost? Well, first we need to kind of set some ground rules here. And while every compressor is different, what we're going to focus on are some rotary screw compressors, and what we can kind of as an average, you can use 4 cubic feet of air is produced for every 1 horsepower of energy that you input into that system. So for every 1 horsepower that you put into that compressor, you're going to get 4 cubic feet of air out. Now, just a conversion factor here, 1 horsepower equals about 3/4 of a kilowatt. One other thing that we're going to keep in mind is electricity is, of course, you'll know what your cost of electricity is for your given area, but the national average right now is about 12 cents per kilowatt hour. It can be lower than that in some states, and in other states it can be much higher. So the cheaper the energy, the less the savings, but especially when you're in places where you're going to be paying a lot per kilowatt hour, energy savings is a huge, huge deal. We're going to look at, in our example, of course, every factory is different, but we're going to look at a factory that operates approximately 8,000 hours per year, and that'll be for every example. So if we take those numbers and we crunch them down, we get that each cubic foot of air costs you $180 a year. So for every standard cubic foot, you pay $180 per year. So now we've talked about flow, let's talk a little bit about pressure and how it affects the cost of your compressed air. So we're going to be kind of focusing on the 100 PSI range of compressors, 100, 125, 150, 175, that kind of range of compressors. But for every pound of pressure that you increase that system output, you're adding 0.5%, you're basically using 0.5% of system horsepower. So the higher the pressure, the more energy that you need to add to that air. So if we look at an example of a 100 horsepower compressor that's running at a discharge pressure of 150 psi. So you've been running at 150 psi. Let's just say, for instance, it was 1 year to the day, and you've been running at 150 psi. Well, you take a look at your system and you're saying, well, I don't really think we need 150. Let's drop it down to 125, and 125 works perfectly for you. So that means that you're running 25 psi higher than what you really needed. So if we multiply 25 psi times that 0.5% times your 100 horsepower compressor, you end up getting the equivalent of 10 horsepower that was basically just wasted. So when we calculate the cost of that horsepower using the 12 cents per kilowatt hour we discussed earlier, you come up with approximately $7,200 per year that you spend running at that higher pressure. So you can see how by changing the pressure and keep getting your pressure dropped down in your system, you can really save a lot of money. So a way that we've come up with this is just in a nutshell, the things that you want to do to reduce your energy consumption is to reduce the flow, you match supply with demand, and you reduce pressure. You do all this, you will reduce the cost associated with running your compressed air system. So as far as reducing flow goes, there's several ways you can do that. The first is storage, which we'll talk about, flow controls, air treatment usage, appropriate uses. Now, appropriate uses we'll speak on for just a moment, but I don't want to get too in-depth on appropriate uses because we could go all day about inappropriate uses, as well as leaks, and leaks are a big one. So the storage of a compressed air system, a lot of times people will think of the air receiver, but it's more than just the air receiver. It's also the compressed air piping. So your entire system all comprises your storage. It can actually, having the right amount of storage can reduce the system's horsepower that you need. If you don't have enough enough storage, you may be running a higher horsepower than you really need. Adding a receiver and lowering your horsepower could save you a good bit of money. Pressure fluctuations are also a problem. It can damage equipment and your products and your processes. So by having that storage in there, it reduces some of your pressure fluctuations, and it also protects your compressor because it'll keep your compressor from short cycling. Now, if you're not aware of what short cycling is, it basically means that the compressor is loading and unloading rapidly, or starting and stopping at irregular intervals. But a good rule of thumb to keep in mind is 3 to 4 gallons of storage per CFM. So that's a good way to get started, but there are some other ways that we can use, especially if you do an air audit, which basically looks at your compressed air system and what you're using that air for, as well as the pieces of equipment in that compressed air system. And you can make a determination of, this is the amount of storage that I really need for my system. So flow controllers. Now, a flow controller essentially is a high flow regulator. It's a valving system that maintains downstream pressure. So it works just like a typical regulator that you're used to seeing, but it works much faster. So we're able to control within plus or minus half to plus or minus 1 psi, depending on the type of technology used, downstream pressure, regardless of the changes in flow. So let's say you've got somebody downstream and they fire up a sandblaster. It's using a lot of air. Well, now your demand is increased incredibly, really fast. So what you need to do is you need to add more air. Well, these valves will react really quickly, and it'll keep that pressure in that system within plus or minus 1 psi of what your set pressure is. So let's say you need to keep it running at 80 psi. You can have it set to 80. It'll keep it anywhere from 79 to 81 psi, and very stable and with no gradient. So a couple problems with fluctuating air pressure we talked about a little bit. Inconsistent equipment performance. So especially if you've got equipment that's very sensitive to the changes in pressure, it can have an effect on your performance. Variable product quality. If you're using the compressed air for your products, it can change the quality of your products based on system pressure. You can have higher scrap rates. You will have higher scrap rates if you've got your pressure bouncing around all over the place. You'll have increased maintenance costs due to equipment failure. You can have premature equipment failure, which will lead to those increased maintenance costs. Higher operating costs because you're running at a high pressure than a low pressure. Interruptions in production schedules as well. So typical system, you're going to have this pressure gradient throughout the system. And mass stays constant, the density decreases, and the volume increases as that pressure drops and it goes through the system. So when we install a intermediate controller or a flow controller in the system, we now have intermittent storage. So as you'll notice in the diagram, we are putting air into our receiver at around 110 to 100 psi. So that's the pressure band that compressor is set to. So it goes from 100 psi up to 110. It will then unload until the pressure drops to 100, and it will start the process all over again. So the flow controller is reading downstream pressure, and you're maintaining that 80 psi. So it's letting that air out at a set rate to keep that 80 psi pressure very constant. Now, the other thing this does is it creates storage, and we'll talk about that a little bit in a second. So it can also be used at point of use. And so right now we're supplying that 80 psi, and this is a good kind of graphic to show you why we would pick that 80 psi. We've got a piece of equipment that's running at 40, a piece of equipment that's running at 55, a piece of equipment that's running at 60, and a piece of equipment that's running at 75 psi. These are the pressures that they require. Well, right now, if you've got it set up this way, you're setting it to 80 so that you maintain that 75 psi for that one piece of equipment. But what you could also do is you could have smaller flow controllers on these other pieces of equipment in order to bring the pressure down to what they require. Okay, so if we look at the black line here, and this is our compressed air flow throughout the system or during over a period of time. So as you start at the beginning, and move along, your demand increases, and then you have what is called a peak demand. So we see these two places where we have peak demand. Our compressor capacity is not quite enough, so we're going to have to make it up with storage. Hold back some of that pressure, like in our previous slide, we had 100 to 110 psi in that tank at any given time. Well, because we're only letting it out at 80 psi, that means we've got a little bit left in reserve. And we can use that reserve storage to make up for those intermittent demands. One prime example of this would be, let's say you have a dust collection system in your factory or in your manufacturing facility, and you want to, every now and then, these have to knock the dust off the bags. They also call them a bag house. So it uses a lot of air, but only for a short period of time. Well, this is an ideal situation where you can use the Conservair flow controller in order to basically keep the total horsepower required to a minimum, so that you just use storage to make up for those periods where you're just using a lot of air, but only at a short period of time. So this is basically how it works. So if we look at a steady state situation, or when you just put a air receiver into a system, so air's coming in at a certain pressure and it's going out at basically the same pressure. There's going to be a very, very slight difference going out. But you do have pressure drops throughout the system, which will cause a little bit of storage. But now, when we add our Conservair flow controller, we're creating a dam. So what we're doing is we're letting the pressure inside that vessel rise to that 100, 110 psi range, and then we're letting it out at 80. That means that if during those peak demand areas, we have the area between the purple line and the blue line, that is all storage that we can use for intermittent demand situations. So another way we can reduce flow is air treatment usage. So air drying and moisture removal. And we'll get into depth on these, but basically this is just what you're doing to treat that air before you use it. And we'll see that there are several ways that that air gets used that can actually be eliminated or reduced significantly. So first one we'll look at is air drying. And most places will have some type of water removal system other than just an aftercooler and a water separator. So the most common way that water is removed from a system is called a refrigerated dryer. And what a refrigerated dryer does is it cools that air down to around 40 degrees, and then the moisture coalesces out of it, just like the condensation on the outside of a soda can after you pull it out of the refrigerator. It's going to do that exact same thing, but then it's going to run it through a moisture separator, and it's going to mechanically separate that water out of the airstream, and the air continues to move on. Now, that's mostly for people that just don't want any liquid water in their system. I just don't want any water filling up my system, which works fine. But now sometimes you've got situations where, let's say, for instance, it gets too cold in that particular location. Say the pipes run outside and it gets below 40 degrees. So you really need to get the dew point lower. And the dew point is a measure of the amount of moisture in the air. So for that particular instance, you need either a desiccant dryer or a membrane dryer. Now, we're not going to hit too much on membrane dryers today, but we will focus on desiccant dryers. And desiccant dryers need compressed air in order to regenerate the towers. So when we talk about desiccant dryers, these are dryers that are used in applications where moisture content is going to be a lot more important to the user than free water in the system. So that means instead of liquid water, they're worried about the moisture content in the airstream itself, suspended within that airstream. Now that can be for a few different reasons. It could be like, for instance, a customer that's creating microchips. They need to have really dry air. They don't want to be building microchips with wet air. So the other thing is it could be in a cold weather situation or in a refrigerated situation where you have compressed air running inside of a freezer. So you need to remove a lot of that moisture so you don't have any condensation and thereby ice forming. So we have three different main designs when it comes to desiccant dryers. We have a heatless purge, and that basically just uses compressed air peeled straight off the outlet of the dryer in order to regenerate one of the towers. We have a heated purge, and that does the exact same thing, but instead of just putting it straight through the tower, it actually heats that air up, gets it nice and hot, helps remove that moisture a lot more efficiently. And then we have a heated blower purge, and that heated blower purge is going to actually strip the moisture off the beads using air that is fed through a blower and up through the heater. And we'll talk a little bit more about that here in just a second. So the three different technologies we're going to look at today are heatless, heated, and blower purge. Now, each one has its own purge consumption, and while there are different technologies out there, different manufacturers, different marketing, the average that you'll see for a heatless dryer is around 18%. Now, that's for a minus 40-degree dryer at normal conditions. Of course, you can have some differences, but for the sake of argument, what we'll do is we're going to look at 18% on our heatless. We also have 10% on heated, and what that does is you've got purge air that flows through a heater, and that hot air is able to remove the moisture from the desiccant inside the tower much more efficiently than just unheated purge air. You also have a blower purge style dryer. Now, instead of using compressed air as the purge air for the majority of the cycle, it uses ambient air that runs through a blower, goes through a heater, and then regenerates that tower. Now, you do need to cool the tower back down, and you can't use the blower to do that, so that is where the 2%, the average 2% comes from, is when we use a little bit of compressed air toward the end of the cycle to basically cool down that tower so that it's ready to dry air again once we've switched back over to that tower. So if we look at an example of a 500 CFM system, we're going to be looking at 8,000 hours per year, so full-time installation, 12 cents a kilowatt hour. So if we look at a heatless dryer, if you take that 500, take 18% of that, that's around 90 CFM of purge consumption per year. So that equates to about 22.5 horsepower needed for that 90 CFM. And that 90 CFM is only used to regenerate that tower. So it's not going to do any work. It's just regenerating the tower. So out of that 90 CFM is just going back into the atmosphere. That costs you about $17,000 per year. And so if you look at a 5-year return on investment, and you're paying $85,000 over 5 years, yes, some of these energy saving options are definitely going to be interesting to you if you're interested in a return on investment that quick. Now, the heated dryer, it also has a heater involved with it. So if you'll notice in these calculations, not only does it have the 50 CFM purge consumption, which is 12.5 horsepower power input for that, we also have approximately $3,025 to run the heater for the year as well. So the total cost to run a heated style dryer is $12,525 a year. So you're looking at a savings of around $22,375 over 5 years. So you've just by switching to that heated dryer, you've saved a lot. Now that doesn't take into account the initial investment, but typically you're not going to spend no more than a few $1,000s more on the heated style dryer. The blower purge dryer, it uses 10 CFM purge consumption, so much less purge air. It's only 2.5 horsepower, and it uses about $1,900 in purge. But then you also have to run the heater and the blower, so that's a little bit more. So you're looking at about $7,310 for the heater and the blower, and so you spend about $9,210 per year. That's almost a $40,000 savings over the course of 5 years over the heatless style dryer. So you can really see the benefits of these energy saving techniques. Now, when we look at other ways that air treatment can actually remove air from the system, another very big one that people don't think about a lot are drains. Now, when we look at what a standard timer drain, what you have on a standard timer drain, you have 2 knobs on there. One is going to be for the interval. That's going to be how often do I want this valve to open? And the next is going to be duration. So how long do you want the valve to be open? Well, if you're using one of these and you're only getting water out, that means that some water is being left in the system, which means that you're actually accumulating water. So you actually have to set them where a little bit of air does come out. And if you're setting it every day and really fine tuning it, you can get pretty good on these. But most of the time, people are going to set them so that when they know that there's no moisture in their system. So there's going to be a good bit of air come out along with that water. So what you can do is you can switch to a no-loss condensate drain, and what this does is it measures the water level. So when the condensate level gets to a set level, what we have is a sensor inside there, that will basically open a valve, allow the water to drain out, but it'll close it before all of the water goes out. So there's no air is lost. It's only condensate that gets pushed out of your system. So another real good way to save some money on air loss and reduce the amount of flow that you have going through your system. Appropriate uses. Like I said, we talk about it for a minute. A very big user of flow in a lot of compressed air systems is inappropriate uses. There's been instances where people have taken hoses and poked holes in them to give them a cooling effect by blowing air on themselves. Very costly, especially once we start looking at leaks. You'll start to see how costly that is. Using compressed air to blow off a work surface, you could do it just as easily with a blower. A lot of other inappropriate uses there. We could go on and on for days about inappropriate uses of compressed air, but you really need to be using it for that equipment that really requires compressed air. If you don't require compressed air, then you can use some other type of technology or a blower or say even electronics for that reason. So like I was saying about leaks, we've got a couple different hole diameters here, and just to look at 100 psi, if you run a 100 psi system, of course, if you increase the pressure, the flow rate's going to increase coming out of that hole. But if we look at just a 1 millimeter hole in a 100 psi system, we're losing about $400 a year, $404 a year. So a single 1 millimeter hole. So as in our example, what I was talking about before, if somebody goes poking a bunch of holes in a 1/4 inch air hose, that's a lot of 1 millimeter holes. And so you can see that they could you're probably just throwing their salary away because of how much air they're wasting every year on your electric bill. A 3 millimeter hole will cost you about $4 grand, 5 millimeter hole, 10 grand or 11 grand, and a 10 millimeter hole is going to cost you about $43,000 a year. So of course, the size of the hole gets bigger. It's more easy to spot. A lot of times you're more apt to fix larger leaks, but they start small. And a lot of times, especially if they're in places where you don't really notice them, you may not ever even think about it. You might even hear the leak and nobody really thinks to fix it. Well, it's just leaking a little bit, no big deal. Well, according to the Department of Energy, 26% of all compressed air leaks out of the system and back into the atmosphere. So 20% of all compressed air generated leaks out of the system and back into the atmosphere. You can check for leaks by doing a simple air audit. This is how much we should be using. This is how much we're putting in. And then you can also listen for leaks using an ultrasonic leak detector. And basically, it's just a listening device that will listen for those leaks. So you would pressurize your air system, you go around, follow it around, and then you can actually hear where there are leaks. So now we'll look at matching up our supply with our demand. So how much are we using, which is our demand, and how much are we producing, which is our supply. Now, I will say there are a lot of different types of compressors. There's piston compressors, there's scroll compressors, there's centrifugal compressors. But today we're really just going to look at the oil-injected rotary screw or rotary screw compressors. But some of this argument can be made for the other types as well. But we're really just going to focus today on the oil-injected screw. So an oil-injected rotary screw is two helical rotors, a male and a female, and they work in opposite directions. And basically, it compresses the air within those channels and decreases the size, which also increases the pressure. So the oil part of oil-injected screw is that it's injected into the inlet, and it's used for cooling, one, to wick away some of that heat, for lubrication, to keep the rotors spinning properly, and then also to seal the gaps between the rotors. So it's got a high capacity and stable flow in varying conditions, different working pressures available. So we typically what we sell anywhere from 100 psi up to 175 psi. They're very compact and they have a very quiet operation, especially compared to piston compressors. So we're going to look at the 6 basic types of compressor controls. And when we talk about compressor controls, what we're talking about is how do we limit the flow or adjust the flow of air coming out of that compressor. So the first type you have is a start-stop, and you're probably familiar with this with your piston compressor in your shop. When you first cut it on, say you're starting from 0 psi or atmospheric psi, however you would like to look at it, you turn the compressor on, it starts up, starts running. If we use our example of our previous 100 to 110 psi example, it'll run all the way up to 110. The compressor will then shut down and then will not start up again until you drop down to 100 psi. Now then we also have load and unload controls. Now when we talk about load and unload, what we do is we cut off the flow to the inlet of the compressor. So for a rotary screw, what you'll do is you'll close an inlet valve that restricts the air. No air can be pulled in, so that would be an unloaded condition. As soon as you open the valve, the air flows through. We're providing air to the system. That is a loaded condition, and it will load. If we use our same example, it will load at 100. It will unload at 110. Modulating. So with a modulating compressor, what we're doing is we're trying to match supply with demand by restricting the airflow coming into the inlet. So as demand decreases, we're basically choking off the inlet of that compressor in order to limit the airflow going downstream. It's really just to match the supply with the demand, but the energy consumption is still relatively the same. We also have dual and auto dual. So for a piston compressor, this would be basically being able to switch it between a start-stop machine and a load-unload machine. Now for a rotary screw, what it means is it runs as a load-unload machine, but the difference is it has a timer inside of it, and if it runs for a preset amount of time in an unloaded condition, it will actually shut down. So that's most compressors are going to be the auto dual feature. You also have variable displacement, and that's going to change the size of the compression area inside your compressor. You can either have spiral valves or poppet valves, and that's just going to change how big your compression area is inside your compressor. Then we have variable speed technology, and that's the one we're going to be looking at the most today. Variable speed speeds up or slows down the compressor based on the amount of air that you're requiring at that point in time. All right, so if you take a look at a typical load and unload machine or auto dual machine, the first thing we're going to notice is if I pull out my pen here, you'll see this is kind of the start. What we're showing here on the top is the PSI, and starting right here, these are the kilowatts. So when you fire up the compressor, what's going to happen is pressure is going to start to build. You're going to jump up in your kilowatts real quick, but then as the pressure starts to rise, it'll slowly rise up, because as you're increasing that pressure, you're increasing the power input. Once you reach this line right here, basically you've reached your set point. The compressor will then unload. The power drops down to the unloaded power. So this is what you'll see right here. That's that unloaded power, and I apologize for my drawing. I'm not very good. But you'll see that unloaded power, and that's that little stair step. So that little stair step is actually where the compressor is running on a timer unloaded. Once it runs for a set period of time, it will unload, or it will basically shut down the compressor. Now when we reach this point right here, our pressure is dropped to our load point. So we load back up. And we repeat the process all over again. So with this typical load-unload machine, you're going to have an energy consumption that consists of about 75% of your total cost of ownership. So now we'll go and we'll look at a variable speed drive. Let's take a look at the variable frequency speed compressors now. And they match the compressed air supply with the system demand. And they do that using a variable frequency drive. So what we have is we have our controller on the compressor. The controller is reading the outlet pressure. So let's take our example, and let's say we're going to have 105 psi system pressure. We want to set it to 105. So the pressure starts to drop. Okay, well, the variable frequency drive is now going to be instructed from the controller that, hey, our pressure's dropping, we need to speed up. So it'll speed up that motor in order to maintain system pressure. Now, if the pressure starts to rise over that pressure, it'll tell the controller. The controller will tell the variable frequency drive that, hey, we need to slow down. So it'll slow it down. And most of our compressors are going to be able to slow down to within 20% of full load capacity. So if somebody, for instance, stops using air, it'll basically ramp all the way down to that 20% mark, and then it will finally shut down and wait until you start to use some air. But the importance of this is that we're matching that supply with the demand, and we're saving about 25% of the total cost of ownership over a regular load, no load compressor. So that's 25% of the total cost of ownership, and that really depends on the size of your compressors that you're using, but it can save you a tremendous amount of money. Okay, so real quick, I'm going to talk about cycling air dryers. The thing about cycling air dryers is you're varying the energy input in order to treat the air based on flow and ambient conditions. So most refrigerated dryers are going to be the non-cycling type, and if you look down here, it's kind of represented here in this graphic. This would be like a standard non-cycling dryer, and a non-cycling dryer runs all the time. So it runs from the time you turn it on to the time you turn it off when you leave the building at night. A cycling dryer will actually turn off and on based on ambient conditions. If it's a nice warm day, you don't need to cool the air quite as much because you're removing enough moisture to keep it below 50% relative humidity. So you would be able to turn that dryer off and on. And it also has the ability to stop the dryer based on flow. So there's a flow switch in there. If the flow going through the dryer stops, it will actually shut the dryer down. And you're not using any energy because you're not using any air. Now, a non-cycling dryer, if somebody forgets to turn it off, even though you're not using any air, it's going to continue to sit there and run. Okay, so the final thing we're going to talk about as far as reducing your cost on your compressed air system is reducing the pressure. So the first thing you want to do is you want to determine the minimum pressure required. That's going to determine what kind of pressure level you need to set your compressor to. So you need to look at your different pieces of equipment in your facility, and based on the pieces of equipment that you have, you can determine this is the system pressure we have. Now, in order to supply that piece of equipment, you do have pressure drops associated, so you're not going to be able to run at exactly the same pressure as that piece of equipment. You're going to need to run a little bit higher, but in order to reduce cost, you can reduce the pressure drops in the system. So you can do that a few different ways. You can use low friction piping and fittings, use low pressure drop air treatment equipment. And then also another big thing that people always forget is the maintenance on these. If you don't maintain your filters and your equipment, the pressure drop will increase over time and can cause a lot of problems with your system. All right, so when it comes to filters, filters are a big thing. They're in almost every compressed air system. And you want to look at a few different things. You want to make sure that you're removing the contaminants that you need to for your process or your piece of equipment. So a lot of times they will specify what micron level you need to achieve for that piece of equipment. So we sell 1 micron and 0.01 micron types of filters. There's either particulate, which gets rid of any kind of dust particles, or other small solid particles. You also have coalescing filters. Now the coalescing filters, they remove oil. And you also have adsorbing towers or adsorbing filters, and these are impregnated with carbon to remove oil vapors. So the other thing you want to look for after you've gotten the right filter is you want to have a low pressure drop across that filter. In Pneumatech filters, we have a very good pressure drop, both dry and wet. You want to make sure that they're reliable so that they're going to last for a good period of time, and you want to make sure that they're easily maintainable. You want to be able to change those elements out with not a lot of effort. All right, when it comes to piping and fittings, I really recommend extruded aluminum pipe. It's very light. It's about 1/5 the size of a typical galvanized pipe or steel pipe that you're used to in the past. Some of the old piping systems doesn't require a lot of knowledge. You don't need to know how to thread pipe. The fittings are very easy to use. Simple tools. A single person can install a system with this instead of having multiple people for that heavy pipe. It does have a very low coefficient of friction, and that's going to reduce your pressure drop both inside the pipe and through those fittings. And it's incredibly reliable and leak resistant, so it's going to prevent those leaks from happening. And the good thing is if you do get a leak, it's very easy to fix. It's not nearly as hard to replace as conventional pipe. Our particular brand is AirNet. It is a very good piping system, and I highly recommend it. If you'd like to know more information, as I said at the beginning, you can always visit www.pneumatech.com or www.cp.com, or just give us a call, 800-336-2285. I'd like to thank everybody for visiting. We're now going to go into our question and answer segment of the webinar. And hopefully if you have any questions, we can try to wrap them all up now, or you can always send them to us as well. Thank you.
All right, Ben, thank you for that presentation. Now let's take a look at some of our audience questions. As a reminder, if you would like to ask a question, just type it into the lower section of the Q&A window and click Submit. Looking at our first question, you mentioned energy-saving features on desiccant dryers. Can you elaborate more on that?
Sure, yeah. When we talk about desiccant dryers, there's one main energy-saving feature, and I think it may be called something different for different manufacturers, but we call it dew point demand. And what that does is that that monitors the water content in the air as it leaves the dryer. And what it can do is at the end of the purge cycle, if you're actually drier than what you need your air to be, it'll actually stop purging and continue to dry on that tower. Now that's dew point demand. Now we also have another proprietary software called Pulse Purge Regeneration, which is used on externally heated dryers only. And it basically uses that hot heated air to increase the contact time by sealing it inside the vessel during the purge cycle. So it seals it in there at about 60 psi, lets it sit and absorb as much moisture as it can, and then it actually blows down the tower that way. And we can save almost up to 50% energy savings using Pulse Purge Regeneration.
Awesome. Thank you. So next question. Is having both a variable speed drive compressor and a flow controller in your air system beneficial?
That's a very good question, actually. Our regional sales manager and I were just talking about this today. Yes, it is beneficial. A lot of people will say that, but with a variable speed compressor, because it's maintaining the pressure, that having an intermediate controller or flow controller is redundant. But we've actually seen in tests at customers' locations where we'll actually have the VSD running with a flow controller. Then we'll actually bypass that flow controller and basically run some tests, and you actually see a large energy savings. And that's because you're basically just balancing the pressure. You're cutting out those peak demands with that intermediate controller, and it's doing it in a different way than what the variable speed compressor is doing. But you'll hear different schools of thought, but we've actually done the tests, and we know it does save energy.
Great. Next question. What is the best method for leaks detection?
Best method for leak detection? Ultrasonic testing is good. The other thing is just to do an audit first and then actually see how much air you're losing. And then that'll also give you an idea of where you want to start looking. But yeah, ultrasonic leak detection is probably the best for very small leaks. Large leaks, of course, should be pretty easy to find.
Okay. And next question. Could you please advise on air temperature requirements for regenerating a blower purge tower?
Air temperature requirements. We're coming out of the heater. You're probably looking at somewhere around 300 to 400 degrees approximately. Once again, for different manufacturers, it's a different temperature. But typically what we want to do is we want to get the bed temperature up to around 250 degrees, and that's in the middle of the bed. We want to get it up to 250 degrees before we start cooling it back down.
Okay. Next question. How can I monitor my energy savings?
To monitor your energy savings, there's a couple different ways, but the first thing you want to do is do an air audit, and that's going to look at how well are you doing right now, and where can you improve. So we have distributors all over the United States, Canada, and Mexico that can come to your location and actually perform an air audit and be able to give you some ideas on what are some ways that I can save some money and some of the equipment that you could possibly invest in order to save a lot of energy savings. Now, once that's done, when you're actually wanting to do the monitoring portion of that, you can do it in a couple different ways. You can do another audit just to kind of follow up and say, okay, let's see how our energy usage is now compared to then, and then you make the comparison. Or if you wanted to do it, keep it real time, we have some equipment that can actually log that information, what's called of our lead air system, which can actually connect to your compressor system and to your compressed air system and monitor that energy on the energy savings on a real time basis.
Okay, thank you. Another question from the audience. Is it possible and worth to retrofit existing compressors with variable speed controls?
It is possible. There are companies out there that do it. I don't recommend it. It's a lot of investment onto a compressor that was not designed to be variable speed. But there are people out there that do it. We don't personally. But yes, it is possible. But honestly, for the amount of money that you're going to put into retrofitting a existing compressor with a VSD drive, my suggestion would be to go ahead and invest in a variable speed frequency compressor.
All right. Let's take a look at one more question. What is the advantage of using a pre and after filter?
A pre and after filter on a desiccant dryer is 100% necessary. First of all, you can't have any oil get into your desiccant air dryer. If you do, it coats those desiccant beads and will never come off. So the more oil that you get up in there, the less surface area you have to actually dry your air. Now, the reason for the after filter is the after filter actually picks up small particulate dust from those desiccant beads. So that keeps any dust from going downstream. So that's why you have a pre-filter for oil before and a particulate filter for dust afterwards.
All right. Looks like we're going to wrap up the Q&A right there. If we did not get to your question, someone will be following up with you soon with an answer. Once again, Ben, thank you for your presentation and your time today. And thank you to all of our audience members for joining us, and have a great rest of your day.